Today's topic, the natural logarithm. F of x is ln x is the inverse function of e to the x. And I have stated this more than one time this semester. So how will today go? Well, I will begin by reminding you about a general logarithm, log base a, where a is positive, not equal to 1, and then some properties of logarithms. Then we will move into the calculus, differentiation, and this will be focused on ln x, together with functions that, say, have ln x somehow in them, but then product, quotient, chain, things like this, okay? Then we move into something called logarithmic differentiation, which is when you don't have any logs, but you bring a natural log into the problem to help you simplify, okay? Now, you might be wondering, especially after last time when we focused on derivatives of e to the x, you may be wondering, what about derivatives of log base a or an exponential function with base a? And, well, I will just say this is the very next video, okay? So let's recall some things about generally. We have a base a, positive, not equal to 1, and then this is the exponential function, which I mentioned last time. Now, the base a logarithm, I'll say x is log base a of y if and only if a to the x equals y. And these are inverse function. The log base a is the inverse function of, let's say, a to the x. I'll state it like that. And the way I always remember this, let me get another color. If you're trying to solve an equation like this, you take the base, raised to this power, it equals this, okay? A to the x equals y. Now, because the logarithm and the exponential are inverse functions, we have some wonderful things. So let's see. Over here, I will do, say, g of x is a to the x. And over here, I will do f of x is log base a of x. Okay? Now this chart is what we know, thinking about inverse functions. Well, what do we know this? This is what we talked about last time, and we looked at some graphs of base a exponentials. Well, we know the domain here is minus infinity to infinity, and this means that the range over here is minus infinity to infinity. And similarly, the range over here is 0 to infinity. All positive numbers are possible, or if you remember, these graphs of a to the x, they sit above the x-axis. And this says that for the inverse function, the domain is 0 to infinity. Okay? So you will never, for instance, have a log of 0. You will never have a log of a negative number, no matter the base. Okay, you can only feed in positive numbers into a logarithm. Now, two special ones, and then I will mention some properties of logarithms. Log base e of x, this is natural log. Okay? Natural log. And this is the topic of today once we get into derivatives. And then log base 10 of x, this is just written log, okay? This one the natural log is really, I would say, for calculus purposes, or even generally, it's the most used. In fact, you can write any logarithm in terms of a natural log. We will see that next time. Now, let's get into log properties. And these are very important. Okay, generally in life, and by in life I mean in math and the sciences, wherever you see logs, because every class I've ever taught that involves logarithms somehow, I see students make up their own log properties. And please don't, because not everything is true with logs. We only have a few properties that we may use. Okay, one is if you have a product inside the log, okay, then it turns into a sum. And this is, of course, whenever both x and y are positive. So anytime I write down a property, well, it holds provided what you're sticking into the log is in the domain of the log, which is positive numbers. Okay, so what's another one? If you have a quotient on the inside, this is a difference. And finally, if you have a power, well, the r comes out in front. Now, it's important to understand none of this is derivatives. Even though we have a bring down the power, x to the power minus 1, that's a power rule. That's for x to a power, and that is not this, okay? This is not derivatives, okay? Before we get into calculus and focusing just on the natural log, here are two examples just to practice some of these properties that we just discussed. This one we want to find the log base 8 of 2, and this one we solve for x, and it involves the log base 3. Here, let's say this is equal to some y, then we use this property that really defines the log base 8. It says that 8 to the y will equal 2. Let's write that down. We get 8 to the y equals 2. Now maybe you see the answer immediately. Well, I do, because I think, well, okay, 2 cubed is 8. This would mean 8 to the 1/3 is 2. But if you don't see it immediately, or maybe you have one that's not easily to spot like this, what we can do here is we can write both sides in terms of the same base, which would be 2 in this case. So here we have 2 cubed to the y, and this is equal to 2 to the 1. And now we may, power to a power, we multiply. Okay. Now, anytime you have the same base, we may equate exponents. We have 3y is 1, or y equals 1 over 3. Okay. Now, here, this one, log base 3, we want to solve for x. What we want to do is get a single log on the left-hand side, and then we will use a similar property, or the similar property that we did in the first problem. So to get a single log on the left-hand side, well, we see a difference, and we can write that as a quotient on the inside of the log. So we have log base 3 of x plus 1 over x. This equals 1. And now we use this, and I'll even use pink again, that 3 to the 1 equals what's on the inside. So we have 3 to the 1 is x plus 1 over x. Okay? Now we just need to solve for x. Well, we can multiply both sides by x. We get 3x is x plus 1, and then 2x equals 1. Or x is 1 over 2 is our solution here. Okay? Wonderful. Now let's go back to the natural log and learn the derivative. Okay, so we know f inverse of x is ln x for f of x is e to the x. Okay, when f of x is e to the x, the inverse function is the natural log. And we also know that for the e to the x, this function, okay, this is what we discussed last time. The derivative of e to the x is e to the x. So f prime of x is f of x, okay, this function. The derivative of e to the x is e to the x. This is what we discussed. Okay, so now let's use the inverse function theorem. Why can we use this? Well, and this is always positive on, well, this minus infinity to infinity, okay? And so the inverse function theorem, this is an open interval, right? The inverse function theorem applies. We want this, the derivative here. What does the inverse function theorem say? It says it's 1 over f prime of f inverse, let's see, I stated it in terms of a b, so I will state it in terms of a b. This would be 4bn, well, it would be the image of the e to the x, which is the domain of ln x. Okay, now f prime, this is this. The derivative of e to the x is e to the x, so f prime equals f. So this is 1 over f of f inverse of b, right? And look, this is composition. F compose f inverse. This is just b, so this is 1 over b. Okay, and this is for b in the domain of the natural log. Okay, so what do we get here? This is the beauty. The derivative of natural log is 1 over x. Okay? This is what we see, and it really comes from the inverse function theorem, and that the derivative of e to the x is itself e to the x. So now we know the derivative of natural log. It's 1 over x. Here are our first two examples involving derivatives. The first one is a sum of 3 terms. We differentiate term by term. And now you see we know the derivative of ln x. It's 1 over x. So the derivative of 5 times ln x is 5 over x. Now here, technically, if we want to differentiate e to the minus x, is a chain rule where the inside function is negative x. So we have derivative of the outside evaluated at the inside times derivative of the inside function. And then the derivative of 7x is 7. Well, we can just write it this way. This is minus 6e to the minus x plus 7. Okay, now this one. This is a chain rule. We see big parentheses. We see the inside function is ln x plus 2 over x cubed, and the outside function is x to the 7th power. So this derivative, we differentiate the outside, differentiate the outside function. Inside, we put the entire inside function. And then we multiply by the derivative of the inside function. Derivative of ln x is 1 over x. This term is x to the minus 3. So we would bring down the power. Minus 3 times 2 is minus 6, x to the minus 4. And then if you wanted this in a little side box, if you didn't see it, the derivative of 2x to the minus 3, you see multiply. Okay, that's this. You could put the x to the minus 4 in the denominator as x to the positive 4. It's fine like this, okay? So here are our first two examples, and now let's do a few more. Here are two more examples. Now both of these we could really do more than one way. This one I could either do quotient rule or chain rule. I prefer chain rule to quotient rule because I think it's simpler. So I will write this. This is the derivative of x squared ln x to the negative 1 power. And written this way is how I see the chain rule. So now bring down the power like this, okay, times. Now I need to differentiate the inside function. And the inside function is, it's a product, right? X squared times ln x. And so we have first times derivative of the second plus second times derivative of the first. Now, you can definitely simplify some here. This is just an x, right? X squared times 1 over x is x, but also is perfectly fine just like this. Okay, now this one, you can either think chain rule or product rule, okay? Because it's a squared power. So maybe I will do it both ways. Just for practice, for the chain rule, we would bring down the power, okay, like this, put the entire inside function, and then times derivative of the inside function. And here my inside function was ln x, my outside function was x squared, okay? Now, the other way I mentioned is to write this as ln x times ln x. And now you see product rule. So this is way number 2, product rule. We get first times derivative of the second plus the second times derivative of the first. And now you see we do get to ln x times 1 over x. So no matter which way we chose here to differentiate, we get the same answer. Well, as we should, okay? But I did this 2 ways just to illustrate lots of times. Well, even in this one I had some choice. We can attack the same function using a number of rules depending on how we think about it. And while our work may be different, in the end we should have the same derivative. 2 more, and both of these are similar. Both of these are like the last 2 where you could attack them a number of ways. We could look at each of these and say, chain rule, where the outside function is the natural log. But, and that's fine. Okay, I'll just say that right now. But it's easier, in my opinion, to use properties of logs to simplify first. So I haven't yet taken the derivative. I'm just going to work with this. I see inside the log, I see a quotient. Okay, so I can write this as ln x minus ln x plus 3. Now, this is a sum of terms, okay? So when I go to differentiate, well, the derivative of ln x is 1 over x. Now, then I put a minus. Now I'm looking at this term. You cannot simplify this any further. This is without a doubt not ln x plus ln 3. And if you remember, I mentioned that every time I teach a class, doesn't matter the class, Calc 1, 2, 3, or anything else. If you have logs in the class, people will invent their own log rules. So let's get this very clear. This part is definitely not equal to ln x plus ln 3. That is not a property of logs, okay? Okay, hopefully we have that down. So the only thing we can do if you have a sum on the inside of a log is work with it just as it is, directly. So let me erase this non-property, but it is important to understand. Okay, so this part is technically a chain rule, although the inside function has derivative 1. So the inside function is x plus 3, outside function ln x, we get derivative of the outside evaluated at the inside times derivative of the inside function. So we just get 1 over x minus 1 over x plus 3. Okay? This one, again, you could do chain rule if you wanted to, but we can also simplify this using properties of logs. Inside the log, I see a power. So I can do this. This is equal to 8 ln x. And now I'm just differentiating 8 times the natural log, and 8 is a constant. So this derivative is 8 over x. Okay? Maybe as a comment, what would happen if you did do a chain rule on this? Because you might think of that without thinking about simplifying with log properties first. If you use a chain rule, we should get the same answer. Okay, well, we take derivative of the outside, evaluated at the inside, times derivative of the inside function. And now you see these are the same because this is the 8x to the 7th divided by x to the 8th, which is just 8 over x, okay? We got the same answer. Chain rule. This will be my last example before we move into logarithmic differentiation. We want to find an equation of the tangent line to this function at x equals 0. And this is one of the exercises in the text. Okay, well, what do we know? We know a point on the graph and on the tangent line would be, let's see if I change this to call it f of x. The point would be 0, comma, f of 0, and then the slope is the derivative evaluated at 0. So maybe I'll do the point first. What is f of 0? Well, f of 0 is ln of 9 over 9, which is ln 1, which is 0. So here, 0, 0 is on my graph and on the tangent line. Now we need the derivative. Well, this is kind of like the last two we did, where we could just start with a chain rule where this is the inside function and natural log is the outside function, but for me personally, I think it's simpler to use a property of logs first and break this quotient on the inside into a difference of logs. So maybe I will do this here. We know f of x is ln 9 plus x squared minus ln 9 minus x squared. Ooh, I almost ran out of space. Okay. Now it's a little bit easier to calculate the derivative, but just as I mentioned in an example I had up here, I cannot split this any further, and I cannot split this one any further. Okay, when you have a sum inside the log, you just work with it. Okay, so then f prime of x, this is chain rule, derivative of the outside evaluated at the inside times, well, the derivative of the inside function is 2x. Maybe I'll write that up here. Okay, now this one, subtract. Derivative of the outside is 1 over x, evaluated at the inside, okay, times derivative of the inside function. Here the inside function has derivative minus 2x. So we get 2x over 9 plus x squared plus 2x over 9 minus x squared. Okay, well, what's the derivative at 0? The derivative at 0 is, this is 0 over 9 plus 0 over 9, 0. So my slope is just 0. So what is a tangent line here? It seems like a lot of work just for this tangent line because we have point is the origin, 0, 0. Slope is 0. My tangent line, y minus 0 is 0, x minus 0 is just y equals 0. The last topic of today is called logarithmic differentiation. And this is a technique that can be useful when you want to find a derivative and the function involved has products, quotients, and exponents. And here's the basic idea. We will begin, well, we take the log of both sides, natural log, okay? Then we use properties of logs to simplify first. And let me underline this because this is an important part. We simplify first before differentiating. And the idea is that, well, we know 3 properties of logs. A quotient on the inside turns into a difference of logs. A product on the inside turns into a sum of logs. And if you have a power on the inside, well, we multiply by that power. Okay, we saw these. But these 3 properties of logs are what make logarithmic differentiation a nice technique when we see products, quotients, and exponents. And here is the first example that we will work. I will say this function we can certainly differentiate without logarithmic differentiation. We may quotient rule, right? Where when we go to differentiate the numerator, it's a chain rule. And when we go to differentiate the denominator, it's another chain rule. But we will use this technique to illustrate logarithmic, or use this example, I should say, to illustrate logarithmic differentiation. Then we will get into some more examples. So we begin by taking the natural log of both sides. This would be ln of x plus 1 to the 4th over x cubed plus 8 to the 5th. And then here comes this part. Simplify first. This part is where inside the log I see this complicated product, quotient, or power thing. Here I see a quotient, and then I also have some powers. And my first step is to break this into a difference of logs. This would be ln x plus 1 to the 4th power minus ln x cubed plus 8 to the 5th power. And now, one more step is, maybe I'll copy ln y. This difference, you see I have powers inside of the log. So the first power I may write like this, and the second power I may write like this. And this is as simplified as I can make this, okay? But now we're in really great shape because both of these terms are quite simple to differentiate, okay? Much simpler, at least in my opinion, than this thing. Now, but we cannot forget to differentiate the left-hand side. This is really a composition where the outside function is the natural log and the inside function is y, and y is a function of x. Okay, so here we go. Now let's differentiate. Derivative of the outside, evaluated at the inside, times derivative of the inside function. And now so that I have differentiated left-hand side. Now let's differentiate this. We have a 4 times. When we differentiate ln x plus 1, we get 1 over x plus 1, and then times 1, which is the derivative of this inside function. Then we have minus 5, derivative of natural log is 1 over x, and then times derivative of the inside function. Now, we are not finished, okay? So this is not a time to stop and walk away and turn in your test or whatever, because we have not finished solving for y prime. We have this part, and we don't want to leave y in the answer. So what I'm going to do is multiply through by y. I will have y prime equals y times this, except I need to put back in y so that I have y prime entirely as a function of x. Okay, so let's do that now. Y prime equals, well, it's y, which is this, and then times what I have calculated over here, 4 over x plus 1 minus 15x squared over x cubed plus 8. And this is my final answer for the derivative of y. Here's another example, and this is yet another one we could do if we wanted to before today. We could have done this last time where we were talking about the derivative of e to the x. We have a product of 1, 2, 3 things. We could split it this way and do product rule, and then when we're going to find the derivative of this, it'd be another product rule. We find the derivative of this, chain rule, okay? So all of this is possible, but let's use logarithmic differentiation. Okay. ln y is ln of this. Okay, now use log properties to simplify. I have a product of 3 things. This will be a sum of 3 things. Okay. Now, here we have a power inside. This is 2 ln x. This one, look, this is where we use the fact that ln x and e to the x are inverse functions. So ln of e to a power is just the power, 3x. And finally here we bring the power outside of the log like this. Inside we had x squared plus 4 cubed. We can bring the 3. So this was all log properties. and this is still ln y. Now I'm ready to differentiate. Derivative 1 over y times derivative of the inside function. Now I differentiate this, and it's a sum. It's term by term. It's much simpler than a product rule. Here, 2 over x. Derivative of 3x is 3. And finally, this, we have a chain rule. We have 3 times derivative of the outside evaluated at the inside times derivative of the inside function. Now my final step, just like in the last problem, we must multiply through by y and make sure we write y as a function of x, so that y prime is a function of x in the end. Y prime is, well, it's y times this, which is 2 over x plus 3 plus, this is 6x over x squared plus 4. Okay? This was logarithmic differentiation. We see in this example function raised to a function. This is a wonderful time to use logarithmic differentiation. Okay? So we take ln of each side. This is ln of is 1 plus 3x squared raised to the square root x power. Okay? But now you see inside the log, I see this, I see it raised to the x, square root x, excuse me. So I may bring this using the third property of logs. Here, this is square root x times ln 1 plus 3x squared. This is ln y. Well, I'm about to differentiate both sides, okay? But what I see here is this times this, one function multiplied by another. This is product rule, okay? So differentiate the left-hand side, derivative of the outside evaluated at the inside times derivative of the inside function. Now I differentiate this, as I said, product rule. It's the first times, well, the derivative of the second, and this part is a chain rule. The derivative of ln x, 1 over x, so we put 1 over the entire inside function, and then we multiply by the derivative of the inside function. So far we have first times derivative of the second. Now second times derivative of the first, which is 1 over 2 square root x. Or you could write this to the 1/2 power, and then it'd be 1/2 x to the minus 1/2. This would be fine too. Okay? Now the final step is just multiply through by y and write y as a function of x. So we have y prime, it's y times this sum, which is, maybe I'll write it this way, 6x square root x, or you could write this as x to the 3/2 power. It's fine. It's also okay the way I'm writing it. It's multiplied, and then plus ln 1 plus 3x squared over 2 square root x. Okay? Oh. So this is the derivative of y as a function of x. Logarithmic differentiation really likes things like this. Function raised to a function. And once we get like the trig functions, we could do x to the sine x, or sine x raised to the tangent of x, or something like this. All kinds of function raised to a function using logarithmic differentiation. Okay, So ln y equals ln of x to the ln x. And really the only simplification I have here is I have an exponent or a power on the inside. So this is ln x. This is the power, and then times ln x. Then we differentiate both sides. Well, in fact, this is something we already differentiated, right? We differentiated ln x squared, but now we're using that as one step in the problem. When I differentiate the left-hand side, again, it's a chain rule, 1 over y times y prime. And here, I prefer chain rule on this too. This is 2 ln x times 1 over x. Now we just solve for y prime by multiplying through by y and writing it as a function of x. So we have x to the ln x times 2 ln x times 1 over x. This would be y prime in this example.